It is possible to be creative in divisibility test by Anna Gerardina Foglino. Hi to everybody, I'm happy to share with you this work. Which pictures can we obtain? What are and how it looks like the factorization of Harshad numbers with Vedic method? The factorization of numbers near the power of 10. The particular factorization using the sutra by one more the one before. Some considerations. Thanks to the visual pattern of divisibility, we can easily explain also to young children or students the correspondence between numbers and divisibility through the pattern found. The definition of divisibility is that capacity of number to being evenly divided without remainder. So, the prime numbers are the numbers which are only divisible by themselves and 1. Let's now see the pattern of some numbers. Divisibility by 2. One number is divisible by 2 if and in 2, 4, 6, 8 of 0. If we draw the pattern in the time point circle, we obtain a pentagon. Divisibility by 3. To find if a number is divisible by 3, we do the sum of digits. If the sum is divisible by 3, then the number is divisible by 3. For the pattern, we write the timetable 3, 6, 9, 12, and so on. Then we do the digit sum and we obtain the code 369. We draw this in the 9-point circle, and here we obtain in very clear and visible manner then the number divisible by 3 as the sum of digits 3, 6, or 9. We can also draw other nice type of graph to show the divisibility by 3. In the first one, we have the line of 3 times table. In the second one, we show the trend of the code 3, 6, and 9. Divisibility by 4. We take the last 2 digits and we check if they are divisible by 4. If yes, the number is divisible by 4. Or we sum the last digits and twice the second. If the sum is divisible by 4, then the number is divisible by 4. We take the 4 timetable, 4, 8, 12, 16, and so on. And we consider the ending figures and we draw the pattern in the 10-point circle. And we obtain the 5-pointed star. We find that the number divisible by 4 are the even number 2, 4, 6, 8, 10, and they are 5, and we found in the circle of numbers. If we like go on with the numbers over the 4 timetables, we go around the circle and we have interesting things. We have a clear image in the next pictures. Here we saw that in the first circle we have 4 age. In the second circle we have 12, 16, and 20. If we add 20, we go in the third circle with 24 and 28. And we go in the fourth circle with 32, 36, and 40. If we add another 20, we go in 44, 48, 52, and so on. And divisibility by 5. A number is divisible by 5 if ends in 5 or 0. So, in the 10-point circle, we get a line from 10 to 5, and this is very easy to remember. Divisibility by 6. 6 is equal to 2 times 3. In this case, the numbers have to satisfy two conditions, divisibility by 2 and divisibility by 3. and we report the first circle corresponding to the divisibility by 3, the 9-point circle, and the second circle, 10-point circle, for the divisibility by 2, number that ends in 2, 4, 6, 8, and 0. That means that the even numbers with digit sum 3, 6, 9 are divisible by 6. Divisibility by 7. We have two ways. We can use the Cadica method. We find the Cadica that now is 5. Then we multiply the last digit for the Cadica, that means for the 5, and we add the digits prior to the last digit. We keep doing until we reach a number that we already know is divisible by 7. Or we double the last digit and subtract from the number, so the number is divisible by 7 if the number obtained is divisible by 7. Here, the nice picture of the 10-point circle in which I've shown all the ending digits. It is interesting to see the line of the 7 times table that I do until 140 and the trend of the 7 times table digit sum. We see the repetition pattern with the decreasing sequence of odd numbers and even numbers alternately. Divisibility by 8. We take the last 3 digits and we check if they are divisible by 8. If yes, the number is divisible by 8. Or we sum the last digit and twice the second, last, and for the third last digit. If the sum is divisible by 8, then the number is divisible by 8. For the pattern, we take the 8 timetable, we consider the ending figures, and we draw the pattern in the 10-point circle. We obtain a pentagon. Looking at the pattern in the 10-point circle expanded, we see that the first 5 numbers of the 8 times table are 80, 16, 24, 32, 40. And we add 40 to obtain the other numbers. If we join the numbers with a line, we obtain a nice pentagonal spiral. Divisibility by 9. When we add the digit of a number divisible by 9, we always find 9. So the pattern with the 9-point circle is 9. Very easy to remember. So all the numbers with some 9 are divisible by 9. Divisibility rules for composite numbers. In general, when a number is the product of different factors, we combine the rules and we can recall the picture of each factor. For example, for 18 equal 2 times 9, we use the rules of 2, even numbers ending in 2, 4, 6, 8, 0, as shown in the 10-point circle, and 9, numbers which digits sum 9, as shown in the 9-point circle. So we obtain the pentagon with the ends of number, and the 9 by the digit sum. The visual patterns of divisibility joins numbers and shapes. It's nice for all age students, and it helps children to remember divisibility rules. Arshad numbers. The Arshad or Niven numbers are curious numbers. They are positive integer and they are divisible by the sum of its digits. Here are some examples. 18 is divisible by 9 and the sum 1 plus 8 is 9. 24 is divisible by 6, and 2 plus 4 is 6. 152 is divisible by 8, and 1 plus 5 plus 2 is 8. Here a table with the partial numbers below 1000. We can do some more example. 399, the sum of figures is 21, and 21 is a divisor of 399. And we obtain 19. One more is 864. The sum of figures is 18, and 18 is again a divisor of this number. 999. The sum of figures is 27, and dividing by 27 we obtain 37. So all the conditions are always verified. This graph shows the trend of partial numbers below 80. If we do the sum of digits of these first 1000 partial numbers, we obtain this nice table. The trend of the digit sum for the partial number below 80 is represented in this graph. So we saw from 1 to 9 is a line, and then they become smaller until 9 to 8. If we like to represent the digit sum for the partial number below 1000, we obtain this graph, in which we can see the similarity that it repeats even if is not identically. Some more information we can obtain if we count the frequency of each digit from 1 to 9. The high is the 9 with 38%, then we have 15%, the 3, and 14% is the 6. The other are between 6 and 5%. It's also nice to represent a partial number pattern using the 9-point circle. So we have the first 10 partial numbers, and we see that all the numbers are dot. Then the first 20 partial numbers, and the first 30 partial number. As we see, the 9 frequency is more than other numbers. We can go on with the representation of a digit sum of the partial number, and here they are the first 80 partial numbers. So we obtain these pictures, and in pink the last 10 partial numbers. Here an idea of Vedic factorization. We have a number S, and we want to find R and U that are the factor of this S. With Vedic maths, we know that S can be equal A, B, two group of digits, and we can find an R that is equal A plus little b, and U equal S divided by I plus little b. Mostly this b is equal b uppercase or is factor. With the traditional factorization, we have to divide S by all the prime numbers until the root square of S. In Vedic method, we have less attempts because we start from A plus 1. Example: S equal 9506. We want to find the product between R and U, that is S. We divide S into parts, A equal 95 and B equal 6. To find the factor R equal A plus little b, we start with B equal 1. So 95 plus 1 is not a divisor. 95 plus 2 is the divisor. So in only 2 attempts, we find the factor r equal 97. Instead of the root square of 9506, that is about 97 attempts. Now we can find u, that is s divided by 97, and we obtain 98. So we have that 9506 is the multiplication between 97 and 98. The little b in this case is equal to, so 2 is also a factor of 98, and we have 98 equal to multiplied 49. We can do all the factorization. 9506 equal 2 times 7 times 7 times 97. Now we can use this type of factorization of one of Arshad numbers that we remember are numbers that are divisible by the sum of its digits. In this case, we have 22, 23, we have 2, 2, 2, and 3, and we find 9. It's a divisor of this number. Let's try to use this basic factorization with Arshad number 2223. We want to find this s equal r times u. We divide the number into two parts, a equal 22 and b equal 23. To find the factor r equal a plus little b, we start with b equal minus 1. 22 minus 1 is not a divisor. 22 minus 2 is not a divisor. 22 minus 3 is a divisor. Good. So in only 3 attempts, we find the factor r equal 19. Now we can find u equal s divided by 19, that is 116. In this case, the 3 is also factor of 116, and that is equal 3 multiplied by 39. So we have 2223 equal 19 multiplied by 116. We can go home with the factorization, and we have 2223 equal 3 times 3 times 13 times 19. For some types of numbers, with the Vedic sutras, the factorization can be easier. For example, we want to find the factorization of numbers near the power of 10, where we use the sutra vertically and crosswise. We take the previous example, 9506, and 6 is 2 times 3, and so we can factorize using 95 plus 2, that is equal 97, and 95 plus 3, that is equal 98. This is the product between 9506 equal r equal 97 and u equal 98. Let's try with the other special multiplication in Vedic maths with the number that have the first figures that are the same and the last figures that add to 10, 100, and so on. We use, in this case, the sutra by one more the one before. For example, we take 2021. 20 is equal 4 times 5, and 21 is equal 3 times 7. We can do the factorization adding the 3 to the 4 and the 7 to the 4. So 2021 is equal 43 multiplied by 47. Some considerations Vedic maths brings creativity and fun. Connecting divisibility rules and pictures is nice and helps young students. We saw the curious Arshad numbers. Arshad means joy giver. We saw the idea of Vedic factorization. And we saw the simple factorization for numbers near the power of 10. And with the sutra by one more the one before. You can find other study on my website.